And welcome back as we go ahead and dive into astronomy. Now we're going to start off by first taking a quick and simple tour of the universe. So let's have a nice good starting point. Let's look at our home. Let's look at Earth. So we're going to take a brief tour of the universe to get acquainted with the different types of objects and distances that we're going to encounter as we move through this course. So again, we're going to begin with Earth, which is nearly spherical. It's about 13,000 kilometers in diameter, which is a pretty large object when you come to think about it. Not as large as some of the objects we're going to see, but for our reference, for where we are, it seems pretty big. Now, a space traveler who would enter into our planetary system would distinguish Earth from the other planets that we have by the amount of liquid water that covers nearly 2/3 of its crust. And additionally, if that traveler had access to radio or television signals, or maybe they even came close enough to see the city lights at night, they could actually see that this little watery planet might actually be supporting sentient life. If we zoom out just a little bit, we're going to take a look at the moon. The moon, of course, is our nearest astronomical neighbor. It is Earth's satellite, and we, of course, just commonly refer to it as the moon. Now, the image below is going to kind of give us a diagram that shows the Earth and moon kind of more draw to scale. And if we take a look at this, you'll notice how small we actually have to kind of make these bodies to fit them in within the proper scale. Because the moon's distance from Earth is about 30 times that of Earth's diameter, or approximately 384,000 kilometers. It takes about 1 month for the moon to revolve around the Earth. Now, the moon's diameter, just for reference, is 3,476 kilometers, or is about 1/4 the size of Earth. Now, we can start seeing we're getting some distance here, and because we have big distance, that means we're going to start affecting the communication that we can use. So light takes 1.3 seconds to travel between Earth and the moon. Now, if you've ever watched any of the old Apollo flights to the moon, you may recall or may have seen that there was a delay of about 3 seconds between mission control and the astronauts themselves. Well, that's not simply a work of fiction, and it's not because the astronauts need more time to process and produce a response, but it literally took 3 seconds for the radio waves to make that round trip between mission control and those astronauts. And that's, again, just the distance between the Earth and the moon. If we had something even farther away, that time would increase even more. So let's look at distance in the sun just to kind of give us some reference points here. Now, the Earth revolves around our star, which is approximately 400 times as far away from us as the moon was. And we call that average Earth to sun distance an astronomical unit, or AU, because in the early days of astronomy, it was the most important measuring standard. Now, keep in mind that light takes slightly more than 8 minutes to travel 1 astronomical unit, which means the latest news that we could receive from the sun would always be about 8 minutes old. All right, so again, it's 8 minutes. Think about the moon, where we said that took 3 seconds. So just to give you some idea of some of the scaling that we're having to deal with here. Now, the diameter of the sun is 1.5 million kilometers. That's pretty large when we start thinking about that in comparison to Earth, because the Earth could comfortably fit inside one of the minor eruptions that occurs on the surface of the sun. And if we take the sun and let's say, let's shrink it down to something that we are more familiar with. Let's make that the size of a basketball. Well, if we were to hold that basketball in our hand, the Earth would be, by comparison, the size of a small apple seed that is set out 30 meters from that ball. So this should really kind of help give you some visualization of just the scale of things that we're working with here. Now, Earth, of course, is traveling through space. And as you probably know, it takes about 1 year for us to go around the sun. That's why we have our solar year. Now, to make it go all the way around the sun, we are traveling actually about 110,000 kilometers per hour. So that's really fast. Well, why are we going so fast and not flying off? Well, the reason why we're able to do this, and we can participate in this fast moving trip without being aware of it day to day, is due to a combination of a lack of resistance and gravity, keeping us kind of anchored to the planet itself. Now, Earth is not the only body that's in our solar system, because now we're trying to zoom out here just a little bit. Of course, we have our planets and, of course, some other objects that are here. Earth, of course, is one of only 8 planets that revolve around the sun. These planets, along with their moons and swarms of smaller other bodies such as asteroids, dwarf planets, etc., make up the solar system. Now, we can define a planet for now as a body of significant size that orbits a star and does not produce its own light. There is a more specific definition that we can dive into, but for now this will work. And similarly, we can also say if a large body consistently produces its own light, it is then called a star, such as our own sun. Again, these are not formal definitions, but they're enough for us to kind of get started with. Now, what about viewing other planets? Because we just said, oh, there's a total of 8 other bodies here. But what if we wanted to see these planets? Well, we can see the nearby planets in our skies only because they technically reflect the light of our local star. So if you were to look up in the night sky and had a telescope and you want to look like, let's say, at Mars, the light that you're seeing coming off of Mars is actually there because it's actually reflecting light from the sun. Now, if the planets were much further away, the tiny amount of light they reflect is usually not visible to us. The planets that we have actually discovered so far orbiting other stars, so if we wanted to go look at another star system, we can't actually necessarily see that light because, again, they're so far away. Instead, we have found things such as the pull of gravity exerting on the planet stars, or when they pass in front of it because they're blocking the light. This is how we, a lot of times, will detect planets that exist in other star systems farther away. Now, what if we want to view those stars themselves? Well, the sun and all other stars are basically giant, enormous balls of glowing gas that generate vast amounts of energy by the nuclear reactions that happen deep within them. Those other stars that we look at in the night sky, they might look faint where we're at here on Earth, but it's only because they are so far away. If we go back to that basketball analogy, if we looked at Proxima Centauri, which is the nearest star beyond our sun, at 4.25 light years away, if we were to go ahead and place that star relative to the basketball that we had earlier, we'd have to place its corresponding ball 7,000 kilometers away from the basketball that's representing our sun. Just to give you an idea of how far away that other star is going to be. Now, keep in mind, when we start looking at the night sky, there are billions of stars up there. If we look up at the star-filled sky on a clear night, so go out in the countryside, get away from all the light pollution, you're going to see all these different stars. And all these stars that are visible to our unaided eye are actually part of a single collection of stars that we refer to as the Milky Way galaxy. Now, our sun is one of hundreds of billions of stars that make up the galaxy. If we take a sphere and we put it 10 light years around the sun, and we say, hey, how many stars are in here? We're going to find that's 10 stars, nowhere near the size of the galaxy. Let's go to 100 light years. Well, now we have roughly 10,000 stars. Far too many to count or necessarily to name, but guess what? We still are only in a tiny part of the Milky Way galaxy. Well, let's make that sphere 1,000 light years across. Well, now we got like 10 million stars. But again, we still don't have the whole Milky Way galaxy. If we make that sphere, though, 100,000 light years across, we're finally going to encompass the entire Milky Way galaxy. And again, that's just our galaxy. It's not necessarily talking about the universe at large. So let's look at that galaxy just for a second here. Our galaxy looks effectively like a giant disk with a small ball in the middle. If we could move outside our galaxy just for a minute and look down on it, it would probably resemble galaxy NGC 1073, as shown at right, with this spiral structure aligned by the light of hot adolescent stars. And we can also see the shape of this galaxy is kind of a giant wheel-shaped system with a bar of stars across its middle. We'll learn later about these types of galaxies, referred to sometimes as spiral or even spiral bar galaxies. And so this is something that we're going to expect to see if we look at galaxies that are very similar to our own. Now, if we want to wonder about the composition of our galaxy and some of the objects that are out there, from our position inside of the Milky Way galaxy, we cannot see to its far rim. Like, we can't look to the edge of it, not with ordinary visible light, because the space that's between these stars, even though it's very vast, it's actually not completely empty. Keep in mind that the sun is somewhat less than 30,000 light years from the center of the galaxy, in a location that has nothing really to distinguish it around it. Now, that empty space that kind of fills those voids, it's not really empty. It actually has a sparse distribution of gas, mostly hydrogen, intermixed with tiny solid particles that we typically refer to as interstellar dust. Now, this gas and dust will typically collect into enormous clouds, becoming the raw material that is used then for future generations of stars. Now, from our perspective on Earth, what can we actually see? Well, we can see the disk itself of the Milky Way. It's kind of a cross-section, and a lot of times we see it flung across like a great white milky avenue of stars with kind of dark rifts of dust, as we see here in this picture. Now, this interstellar material that might look really close and dense here is actually so sparse that the vacuum in between stars is a better vacuum, technically, than anything we could produce in a terrestrial laboratory. Yet, even though there's all that space, the dust there builds up over thousands of light years. So you have a particle here, a particle there, and it all builds up. That can block the light of distant stars. So astronomers have found that stars and raw materials shine with various forms of light. And because they know about these different forms of light, we've been actually be able to map and develop what our galaxy kind of looks like. Now, again, we just saw what it looked like when it's visible, but what about the unseen, the things that are kind of not being able to be detected? So from these various investigations that scientists have done to really get a good map of our galaxy, we have evidence that much of our galaxy is made of material that we cannot currently observe with our current set of instruments, and we refer to this a lot of times as dark matter. Now, we know that dark matter is there simply from the pull that its gravity exerts on the stars and the raw material that we can observe. But what this dark matter is made of and how much it exists is still kind of a mystery to astronomers. And dark matter is not necessarily confined just to our galaxy either. It appears to actually be an important part in other star groupings as well. And speaking of star groupings, what about star clusters? So, not all stars, like our sun, are actually by themselves. Some are actually in double or triple systems with 2 or 3 or more stars revolving about each other. Now, because the stars in these systems influence each other, multiple stars can give us an insight into different characteristics that we could not discern from single stars, such as our own. And when we do see these stars that are in their systems, a lot of times they are in large clusters, and when they form together like this, we recognize them as star clusters. Some of the largest of these star clusters that astronomers have cataloged contains hundreds of thousands of stars, and they take up volumes of space that's hundreds of light years across. So what does a star cluster actually look like? Well, here's an example of one of the largest star clusters that we know by its catalog number M9. It contains some 250,000 stars, and is seen more clearly from space using this Hubble Space Telescope. In terms of distance from us, this is roughly about 25,000 light years away. But again, you look at this, that's a lot of stars packed into one area. But keep in mind, even though the stars are all there, those stars are not forever. They have a lifetime. No star, in fact, even our own, cannot last forever. Because stars by their very nature produce energy. And energy requires fuel. And eventually, all stars are going to run out of fuel. And our own sun, in fact, has about 5 to 6 billion years left to go on its current fuel life. Now, ultimately, the sun and all stars will die. And it is in their death that actually some of the most intriguing and important processes of the universe are revealed to us. For example, many of the atoms that we use to create different materials or help sustain life were once inside of stars. What happens is a lot of these stars, at the end of their lives, exploded or ejected the material in some manner, and that material was then recycled back into the cosmic reservoir. And so you could really think of yourself as being made out of recycled stardust.